Okay, so before we go to the Python, I just first want to quickly recap in the textbook where we are. So we'll most probably only get to the Python tomorrow, which is not the end of the world, but let's just quickly orientate ourselves where we are in this course at this stage. We're in chapter 3, and specifically we are in chapter 3.9. Okay, so this is where we are at the moment in the textbook. I'm just going to page through this chapter and just talk you through it so that I can just put what you're seeing here into perspective. Okay, so first off, we're busy with one-dimensional problems. The way I'm deriving it is we still assume a full three-dimensional field. We assume a U, V, and a W field for displacement, and we assume W, U, W, V, W, W fields for the weighting functions. Okay, so I'm just deriving it in a more general form and setting because that allows us to get comfortable with the high dimensional stuff without having to have all the mathematical complexity in there. Okay, but the problem that we are is essentially, so we are going through this in the full 3D case, but in the 1D case things would typically simplify to the fact that you only have one strain component that's non-zero, one stress component that's non-zero, and there's some tractions and there's some body forces we could apply. This example we're looking at now, we're only going to be, or that we just look at now, is only applying attractions. Tomorrow we'll also look at where we apply body forces. And I want to do two separate examples there on ones that we've actually had computed before. So the buying on its own weight is going to be the example we'll do for the case of the body force. Okay. So what we know, stress is related to strain is related to displacement as follows, and then the partial volume integral is related to A dx. That's really the implications of the 1D problem. Okay. So in the finite element method, we typically go and we'll divide the structure into multiple elements. We looked so far only by saying let's divide the structure into one element only. So we have one element, and then specifically our elements were slightly different to these. Look at these. These elements only have 2 nodes per element. So there's element number 1. There's only 2 nodes. Ours had 3 nodes. So we looked at the quadratic element, the one that's in 3.9. These elements here in the beginning are all linear elements, and this is what I want you to go through on your own, because this is a much simpler problem to solve than the one we solved and tackled so far. We've already started solving the quadratic ones. And as a fact of the matter is, they're both a joke to do. They're both quite easy and trivial, and it's okay. It's supposed to be easy and trivial because we want to keep the maths easy and trivial and interpretable. So what is important from an engineering point of view is that we keep the maths simple so we don't make mistakes, and we keep it interpretable that we can quickly verify whether things are making sense or not. Okay, so this is what we've done from construction of the finite element approach as we've proceeded. But essentially, this is where we're going to work towards having these multiple elements, and that early next week we're going to look at having multiple elements, and we go up to 1,000, 10,000 elements for a structure. Okay, so that we can start tackling those problems. But for now, let's first make sure we understand one element properly, understand the implications, make sure that we're comfortable with it. There's no point in doing 1,000 elements if the one element is still problematic or is not 100% understood. Okay, so that's essentially what boils down here. Mapping these elements into so each of these elements, essentially then you can think of isolation about them, and we know that in the displacement side they share sort of nodes, and those are things that we'll still talk about as we go along. Okay, so this is just talking in general about element connectivities. Here they talk about shape functions. This is now the example of the linear shape functions, how they look over an element. So this is, make sure that you're comfortable. See, this is how the displacement will be assumed to vary spatially using that shape function, this shape function. And this is really just to get you comfortable on we're taking a linear superposition of these things and essentially build up a displacement field. Okay, so each one will be multiplied with Q1, Q2, Q3, Q4 in the end. When you superpose them all, we get sort of a displacement field out. Okay, and if you do linear elements, you have a linear field. If you're quadratic elements, you have a quadratic field. You'll see the shape functions down in the book for the quadratic elements, but I want you to actually go and plot them and SymPy yourself. So just as a quick example. Okay, but in essence what it boils down to is we write the displacement field as a collection of the n's, the n vector times the unknown q's. So this is u and q, what you've seen before. Here we're doing the isoparametric formulation, x related to x related to this y, the shape functions to the nodal coordinates, and that way to z due to the shape functions. So this is the isoparametric formulation in action, and this is the way I always want you to treat x's. X will always be n1 times x1 plus n2 times x2, and in the quadratic case n3 plus x3. that is what we always be going to do. We're not going to do anything other than just assuming isoperimetric relationship. Okay, here's an example what they do of just saying here's two coordinates in x1 and x2. What is essentially the psi coordinate of this point here and stuff. So please work through this, get comfortable with this. This is not anything difficult, but this is a much simpler example than what we tackled. Okay, so you can work through this and you can see how they relate displacement to strain, same as what this stuff you've seen now. You'll be comfortable with that, the psi dx. And so all of these things are quite straightforward, just running through the mathematics. Okay, end up with strain is BQ, stress is EBQ. So all of these things you would have seen now, and they would fire in your brain. So these things, Nico, I know, man, I've seen them. Okay, the potential energy is not the approach that we follow. We follow more the weighted residual approach, and that's a lot more easy to understand, because there's no point in doing something if you don't fully understand it, and it's usually with the potential energy, the work potential and stuff like that is not always properly understood. And if you take the stationary point of this, you find essentially equilibrium. All of those things are not always trivial to relate directly. So the weighted residual, you know exactly what we did. We solved the sum of the differences squared minimum. Yeah, that's a fact. We just solved that problem, so we don't have to stress about anything else. We know what we did. Okay. So this is just if you were to follow through on the weight. But what I want you to see is, although this stuff in the beginning here might not be relatable, these things that you see here would be exactly what we have came to. You can just verify that for yourself. Nico can say, Nico, yes, these things are definitely what we did. I can see this is exactly what we did. Okay, so this is important to understand. This is now looking at the strain energy, but this is essentially that what you've had there. Only difference is we had a WT there. Here they have Q's because they're following a different approach to derive this. Okay, so don't let this confuse you. We followed more something that's maybe a bit closer related to a sort of a Galerkin approach. Okay. Bottom line, where we are now, so you can see the Galerkin approach, they've written it, there's a Q transpose, we had the W transpose there, and here they have sort of this nodal virtual displacements that they call them, where for us it was these nodal weights, coordinates that we had, and ours was on this side, then we had the Q on this side. Doesn't matter which way you want to write it, like they show here, you can write it by either way, but the point is we took derivatives in respect to these W's, and then boom, 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 we got the equations derived. Okay. So as you go along here, you can see, yes, this is how the stiffness matrix looks for this little linear element, nice 2x2 system. Yes, essentially, if you want to look at some of the forcing terms, here they look at the tractions, and I think these body forces are here, and these things you can follow through. We're going to look at a body force example tomorrow to have fun about that. But now you understand how to do these tractions quite clearly, so you're quite comfortable with that. Here they just go for the multiple element stuff that we'll start looking at next week, the assembly stuff, how to assemble it, what are the properties. Okay, we're going to look critically at that. Already you know the symmetry one, I've highlighted that one you're comfortable with. And then there's also some talk about how to work with boundary conditions. So this is about the elimination approach. We already started with this today, where I eliminated all the known displacements, took them to the other side. We're not going to do the penalty approach, which is my computer's freezing a bit. The elimination approach is what we're following in this course. Penalty approach we're not going to do, so don't stress about that. I don't want you to look at how to enforce constraints, displacement constraints using elimination approach, the penalty approach. This is not what this is all very old school type of stuff. And then essentially, here's just an example where they look at two different materials, applying a point load and saying what's going on. So this is now, you can see a nice statically indeterminate. You need to know something about the material, it will affect the solution. It's nice statically indeterminate problem. Okay, the example we looked at was a statically determined one. But here's now first nice statically indeterminate example problem. Okay, and so you'd be able, well, for one, we're going to look at two in multiple elements next week to make sure we're comfortable with that. But first, let's finish off the single elements in style. Okay, this is an example. If you have a displacement solution, you have a gap, you have to first figure out that you reach it with the load that was applied or not, because then you have to make a decision whether you include this wall or not in your solution. Multiple constraints is just really when you have constraints that are sort of a combination of displacements and unknowns as opposed to just a single one. So in our case, it's Q1 is equal to 5 or Q2 is equal to this. But maybe you have Qs on a roller on a incline that you would like to work with, and then you can work with multiple constraints. In the beginning, I'm not going to formally look at this. We might look at this towards the end of the semester if we have time. Okay, because it is quite interesting, and it's an important point to just understand what multiple constraints are, because it's quite powerful modeling tool. Okay, this is what we've done. Quadratic shape functions now, but you see here, so these things you'll see are going to be quite familiar. Look at that numbering, 1, 2, 3. I'm just keeping it consistent with what they are doing. This is just the choices that people have made. And so we keep it consistent that we always numbered 1, 2, and then 3 in the middle. Okay, so that's just something to pay attention to. Look at those shape functions. Here they're just drawn. You can then ask yourself whether they make sense. We agree with them. But because I've got a 1 here and 0, 0 here, I end up with quadratics. And so it's very simple, trivial polynomials you can go and play with and visualize and see what the implications are. Remember the properties? The sum of n1, n2, and n3 must be equal to 1. Why? Rigid body motion. Okay. Then UNQ epsilon is BQ. So where's the BQ? This is what you'll see. It's just the same derivation that we followed. So my computer is really slow now. You can just see du dx, du dψ, dψ dx. All of these things are familiar stuff that we've done. No problem. Just following the maths. Okay. Following the basic differentiation. This is why I said all of you could start this problem that we've just done. You could have started it on your own and actually derived all of this, because it's really just following basic polynomial and basic vector algebra. Okay, so epsilon BQ, B is then that. Stress is EBQ, that's all the stuff we've seen. We've followed this with the weighted residual approach, and then ended up with our stiffness matrix, ended up with our tractions, and there's essentially, you can see a little bit of what happens with when you have body forces applied. Okay, so this is a traction. What they're applying here is a traction that's quite different. It's a traction on the surface, I think, when they talk here. So our traction that we applied was at the edge. So at a specific tau, at a specific x. Okay, so what they are talking about here is a traction that's along the outside of that element, and a body force which is just sort of something like gravity along. And we'll start looking at these tomorrow, in terms of if we have sort of a body force that we apply. That's what we'll start looking at tomorrow, as it's the last example before we get to multiple finite elements. Yes, it's a nice example that I do. Q1, Q2. This is now taking a thing that's spinning around a point. We'll look at this example on next week, Tuesday. And this essentially allows us to assemble this. What they do here, what I don't like, they don't look at this body force varying linearly with R. As you would expect, they sort of just lump it as a constant. They say, what's the average value? What's the average value? And say, apply a constant and a constant over the element of the body force. We're not going to do that. We're going to apply it properly and apply it as a linearly varying body force along the element and linear varying, and see what things look like. Okay, but this is what the way they did it. They made that modeling assumption, but it was an unnecessary assumption. So we can then compare our solution to their solution and see which one you prefer. Okay, then there's talks about temperature effects. This is really trivial to include in structural mechanics, because it's really just a pre-strain that you have. So if this strain does not result in any stress, if you let the body freely to deform without any restriction, there's no stress involved. And so the stress is the difference between what the stress the stress is related to what is the strain minus the free strain that you wanted to have experienced. And if this strain is exactly the same as that free strain, due to temperature effects, there's no restriction, then the stress is 0. It's like if I just heat the body up and I'm letting it sit out in shape, let it expand freely, then there's no stress that involves. But if as soon as I start pushing it back, or I start to restrict it in a way that it can't, then there's stress that evolves. And this stress component can be quite dramatic, that evolves from temperature effects. I mean, as a matter of fact, lots of mountains are carved open because water goes in between cracks, freezes, and cracks open mountains. So those stresses can get quite large. So it's important consideration. But it's really, luckily, you can see, quite easy to relate, because this is just related by the alpha delta t, where alpha is sort of your expansion coefficient for your material. Okay, so that's a 1 over t kind of units that's got. Okay. Then lastly, in this chapter, there's problem modeling and boundary conditions. So this is just talking about if you have a problem that is, my mouse is now hanging. This is the problem. I have a clamp there in that side, applying a load here. We could simplify this as a symmetrical problem. We're going to start looking at this formally towards the end of the semester, but only in multi-dimensions. So this is just giving you an idea already. There's some symmetry you can do because everything is the same along this axis. If I flip it across, everything stays the same. So this is a symmetric boundary condition. We're still going to look at symmetric, anti-symmetric, and the implications of that, as well as how we can do some funky stuff with that in terms of reducing the complexity and the cost of the model. The reason why this is important is really just we don't want to waste time. We really don't want to waste time. Let me see, my battery is going flat. We really don't want to waste time on solving large problems if we could have solved a much smaller problem quicker. Okay. And so this is just this, and then it's again the problem of the gap. But here's some examples towards the end. Please go and page through them and give them a go. So the one that we've done so far, we've essentially looked at this sort of a problem like this without the body force. This is what we've sort of looked at this stage. Not exactly the same problem, but something related to that. So hopefully this gives you a good idea of where we are in the textbook.